Hello everyone and welcome to today's webinar in the CERDP and ESCCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of this series on behalf of CERDP and ESCCP. I will be facilitating today's call. The webinar will consist of a brief overview of both programs, followed by a list of upcoming webinars in the series. Following opening remarks, we will transition to the technical portion of the webinar. Today's event features two presentations on DoD research efforts related to high-resolution site characterization at chlorinated sites. First, Mr. Murray Einerson from Haley and Aldrich will talk about a direct push optical screening tool for high-resolution real-time mapping of chlorinated solvent DNAPL architecture. Mr. Einerson's presentation will be followed by a brief Q&A session. He will be followed by Dr. Andrew Jackson from Texas Tech University, who will talk about high-resolution delineation of chlorinated solvent concentrations, biogeochemical processes, and microbial communities in saturated subsurface environments. Andrew's presentation will also be followed by a brief Q&A session, and then we will conclude the webinar with an interactive Q&A session involving both our speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions well in advance of the Q&A session. On the slide, we have provided a few suggestions in case you experience difficulties with the broadcast audio. Typically, any delay can be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using that chat box in the lower left corner of your screen. CERDP is the Strategic Environmental Research and Development Program established in '91 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. CERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESCCP, on the other hand, is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESCCP demonstrations is the ultimate transition to implementation and regulatory acceptance of demonstrated technologies. CERDP and ESCCP are complementary programs with much of CERDP research occurring at the lab and pilot scale with occasional field efforts, while ESCCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in CERDP and 5 in ESCCP. The Energy and Water Program area is only in ESCCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapon Systems and Platforms, are CERDP and ESCCP programs managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration Program area. This area has essentially 5 major focus areas: contaminated groundwater, contaminants on ranges, contaminated sediments, wastewater treatment, and risk assessment. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see, upcoming webinars will cover a broad range of topics, including tools for risk-based remediation of unexploded ordnance, coupling geothermal heat pumps with underground seasonal thermal energy storage, the management of energetic and propellant material releases on testing and training ranges. So we encourage you to check this list periodically and sign up for upcoming webinars. You can find information about the upcoming webinars at this link. Registration is now live through the end of the summer. And before we move on to our speakers, I would like to remind you that a copy of the presentation of today's session can be downloaded now from our webinar webpage. And we will have a survey at the end of the webinar, so if you can stick with us till the bitter end, it would take you less than 3 minutes to complete the survey. So we would really appreciate your time and attention to the survey so that we can continue improving. One last thing, for the first time since 2011, the Startup and ESTCP Symposium will be held in Washington, D.C. The dates are November 28th to the 30th. It's a 3-day event that will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is available for the symposium on the Startup and ESTCP website. It is now my absolute pleasure to introduce Mr. Murray Einerson, who is a principal hydrogeologist working with Haley and Aldrich in Oakland, California. Murray has over 30 years of experience as an environmental consultant and groundwater researcher. He has focused his career on developing and promoting new methods and technologies that improve environmental site characterization and in situ remediation. Murray has a Bachelor of Arts degree in geology from the University of California in Santa Barbara and a Master of Science degree in hydrogeology from the University of Waterloo. And with that, I turn it over to you, Murray.
Okay, thanks very much, Rula. Can you hear me okay? I assume that's a positive. So thanks for the introduction, and my presentation here today is on a new technology for mapping chlorinated solvent source areas in 3 dimensions. And this is a completed ESTCP research project, ER 2011-21. And my presentation outline today is I'll share a few words just on conventional or traditional methods of DNAPL source zone characterization that we've had available to us, and they have unfortunately been lacking. And then I will describe a new technology, a variation of laser-induced fluorescence called DyeLIF, and then I'll present the results of our ESTCP field demonstration. So here we are 30 years after the term DNAPL was coined by Stan Feenstra. Before 30 years ago, we didn't really know that there were contaminants like chlorinated solvents, PCE and TCE, that when spilled would migrate to sometimes great depths, even below the water table, where they could be trapped in ganglia and dispersed in fairly heterogeneous fashion in the subsurface. So we discovered that from field research 30 years ago, but for the last 30 years, amazingly, we've had to live with just cartoons or conceptual models or sand tank models of what these residual DNAPL source zones look like or might look like at our sites. And that's because we haven't had high-resolution economical field methods to quickly delineate these residual DNAPL source zones. We have had methods. The traditional methods have been available for 3 decades, and there's early guidance documents, this one dated 1993, that describes some of the common tried and true methods, including direct observation, hoping that you might see the DNAPL in the soil samples. Unfortunately, a lot of the chlorinated solvent DNAPL and other NAPLs are clear, and it's often very difficult, if not impossible, to directly observe DNAPL in the subsurface. Soil concentrations are another recommended method where you use a direct push technology or other drilling tool to collect soil samples and then send the samples or a sub-sample off to a laboratory and analyze for your constituents of concern. And if the total concentration is above a threshold for a partitioning threshold, you likely have a DNAPL or separate phase NAPL present. The problem with that is that the subsample you send to the lab may not be representative of the entire core, or you may have biases during the collection of the soil core, such as poor sample recovery, which is really quite common in subsurface investigations. So there's limitations with using soil concentrations for defining DNAPL in the subsurface. Then there are dyes, so colorimetric dyes, the dye shake tests that have been used, and I think are among the more reliable methods, but also quite time-consuming. And some of the dyes that are commonly used are oil red O, or Sudan 4 is another one. And this is a publication from an ESTCP or CERTA-funded project led by Bernie Cooper. There's a guidance document published in 2014 that describes how to use these colorimetric dyes. You basically have a little vial, you add a little bit of soil that might have a NAPL in it, you add water, and then a bit of an emulsion of this dye and shake it up. And if there's a separate phase NAPL present, the dye will turn red. So it's a colorimetric test. And we used that method as well as others for comparison during our ESTCP project. I hear a lot of times from people, well, what about the membrane interface probe? Isn't that a fabulous tool for DNAPL source zone investigations? And I agree it's a fabulous tool, and I use it a lot to define where I have high concentrations in dissolved plumes, but I tend not to use it in source zone investigations because it isn't diagnostic for the presence or absence of a NAPL phase. Because the membrane interface probe, the way it's constructed, it has a semi-permeable membrane of sintered Teflon and stainless steel. It's heated to 100 degrees centigrade. And if there's VOCs in the soil or water or vapor phase or NAPL phase, it'll partition through the membrane and be taken up in the carrier gas and can be detected. The problem is that it detects volatile compounds, hydrophobic compounds, in any and all phases. It doesn't differentiate for NAPL. So if I want to know where there's NAPL or confirm that there is no NAPL, the membrane interface probe is not going to tell me that. It's a very useful tool, but I tend to use it more for dissolved phase investigations. Laser-induced fluorescence, on the other hand, only detects NAPL, if it's present or not. And until now, you have to require on the innate fluorescence of the NAPL. There has to be PAHs, polynuclear aromatic hydrocarbon compounds, in the NAPL that will naturally fluoresce if they're bombarded with a certain spectrum of light. And that's the whole premise behind laser-induced fluorescence. And fluorescence has been used for years in the oil industry to see if there's pure phase petroleum products in drill cuttings, etc. But some clever researchers 25 years ago at DOD and DOE and a university in North Dakota basically miniaturized and packaged the LIF technology for direct push application with CPT platform. And so in the diagram that you can see here on my screen, with the tool, you've got a fiber optic line and then a little mirror that bounces the spectrum of light out through a sapphire window. And if there's NAPL that contains PAHs, it'll start to fluoresce, and that fluorescence bounces off the mirror and is transferred back to an oscilloscope at the ground surface via a different fiber optic line. So kind of old technology, ahead of its time, but darn it, it still hasn't worked with chlorinated solvents. It does work with petroleum hydrocarbons, NAPLs from coal tar sites, MGP sites. It's a useful technology. It has been geographically limited until about 10 years ago, when Dakota Technology received a license to sell technology and provide this as a service. So there's a whole new generation of LIF that's available, and it really has revolutionized our ability to delineate residual NAPL, but providing that it has PAHs in it. So it's been limited to sites that or it hasn't included sites with chlorinated solvent DNAPL, unfortunately, until now. So the new modification that was the subject of this research project, this demonstration project, was just a little tweak of conventional LIF, but to add a little tiny tube, an 1/8-inch plastic tube, Teflon tube with a little connector, and then a port through which an emulsion of water and a little bit of powder of a fluorescent dye is slowly injected while you're advancing the tool, and that creates a little film against the wall of the probe hole. And if there's any NAPL present or not, no matter what its composition, it'll fluoresce like crazy. So it could be corn oil, it could be any NAPL. It no longer has to have PAHs in it. So that was the idea. We approached ESTCP, they funded us, and we spent a couple years developing the tooling and technology, and then performed a demonstration project, which I'll describe here in a little bit. So this new technology is referred to as DyeLIF, and it's just basically adding a very small amount of an emulsion of a hydrophobic fluorescent dye ahead of the detector, so that you're forcing any residual DNAPL, no matter what its composition is, to fluoresce and therefore be detectable with conventional LIF detectors. Our project included laboratory testing and then some stacked disk or benchtop testing, and then finally field testing. The laboratory testing, we solicited all of our friends and colleagues and regulators to get samples of DNAPL from actual sites that has been weathered in the subsurface, and we got about 24 samples. We analyzed those samples for the chemistry and then the optical response with at least 40 different hydrophobic dyes. And the dyes that we sought out are dyes that are non-toxic and used in the textile industry, for example, for dyeing shoe leather. So Randy St. Germain at Dakota Technology really did a great job of obtaining and testing various dyes with 24 different samples of actual DNAPL. And then this this slide shows some of the testing protocol, because you need, here's the sapphire window, so that's where you're taking your measurement. He created a little bit of a little well around it with this little plastic sleeve, and then would add different solutions of sand and dye and NAPL. And the goal here was to create and quantify an enhancement factor. There is some small amount of fluorescence that occurs from the dye itself, and that's desirable because you want to be able to detect that to show that you're actually injecting the dye in through the tool. There might be some innate fluorescence from impurities in the NAPL. So what we're after here with this calculation of an enhancement factor is just to isolate the enhancement of the signal caused by the addition of the dye. So we recorded this enhancement factor for various combinations of the DNAPL samples and the dyes that we used, and this is described in quite a bit of detail in our final ESTCP report. Randy St. Germain then went out into his back yard and did various stacked disk experiments. So under very controlled conditions, created disks about an inch thick with various combinations of clean sand and pure product, of PCE, TCE, other kinds of pure chlorinated solvents, buried them in buckets, and then in his backyard just drove the tool through the buckets dozens and dozens of times. There you can see the little laser coming out through the window there in the tool, and recorded those results. And here's just a record. If you're familiar with LIF, this is a pretty typical and familiar graphic. But this just basically shows the clear detection of a 1-inch thick layer of PCE amended sand at a 50% saturation, and it was detected perfectly, plus or minus a millimeter at the top and the base of that pure PCE impacted sand in a laboratory test. Note that there's a very sharp contrast at the base of that 1-inch thick layer, which demonstrates, as has been demonstrated at hundreds or thousands of field sites, that there's no drag down of that product as you penetrate it and pass through it with the direct push tool. Now we move on to the field testing, and we found an ideal site in Lowell, Massachusetts, a formerly used defense facility. And it was ideal for us because it was amenable to direct push. And unfortunately, this technology is not yet available for bedrock environments. It's advanced with direct push tooling, so you have to have relatively unconsolidated soil to use it. There was DNAPL at the site and actually collected in monitoring wells and recovery wells that we tested in the laboratory. And there was a lot of existing high-resolution site characterization and a robust site conceptual model. And finally, the DNAPL was pretty shallow, so less than 70 feet depth. And then ESTCP is pretty rigorous with actual validation of our results. So we had to compare our results with this new tool to other measurements as close to where we were making our measurement as possible. And that's kind of a tall order, but we worked with ESTCP and we came up with a program of doing alternating DyeLIF probes and soil borings on 1 meter grid. So we're really getting a pretty saturated coverage in the subsurface. And then further, we split the soil cores and subcored at the same elevation, within a quarter of an inch, and sent some samples for chemical analysis. And then we did subcores for that Sudan for visual dye testing. And then we used the DyeLIF tool on laid out horizontally, like we did at the laboratory, but on site, and we added some dye and the soil to that tool also. So at every depth, we had 3 different measurements from the same core hole. So the first week of our testing was just going to town with our probe, the new DyeLIF probe, followed by a week of soil coring for comparison to the DyeLIF response. And as I mentioned before, those soil cores, subcores were tested in 3 ways with the chemical analysis, the colorimetric dye shake test, and then the benchtop LIF testing. So about as rigorous a program of comparison to other methods as you could possibly develop. So week 1, we're out there now with the new DyeLIF tool and advanced with a geoprobe rig. This basically shows kind of the area that we're focusing our work on. And there's a lot of high-resolution data here and a nice detailed transect further down gradient. And so within this this area of this red box is where we focused our probing. And so the probe holes that we advanced are shown here. And then what's not shown is that at every one of these locations, just less than a meter away, there's a continuously cored borehole where we did those comparative tests. And then this is just a little photo journal of that first week of testing, and it all went quite smoothly. And this just shows some of the equipment that was used, including the DyeLIF tool with the sapphire window there on the right. And the results after 1 week, and not even a full week, but just 4.5 days of work at this site, we probed 25 different locations, and to an average depth of about 70 feet. We averaged 390 feet a day, so a 70-foot hole could be completely explored or probed in less than 2 hours. Our rate of penetration averaged about ½ an inch per second. There was no downtime experienced from repairs or damage to tooling. It was a very small amount of dye that was actually delivered to the subsurface. And we used a geoprobe platform. And after 4.5 days, that DNAPL body, a residual DNAPL, was completely delineated in 3 dimensions, with one exception, and that was a small building that was in the way. And that's just an example log from that particular site showing where there is dye release, which is a good thing. You want to know that we're releasing dye. But then just a small thin layer of chlorinated solvent DNAPL, about 1.5 centimeters thick, that was clearly identified in that particular log and in several different logs. One thing I'll mention here too is that since we're injecting an emulsion and a fluid, we can monitor the injection rate and the back pressure. So the injection rate divided by the back pressure is proportional to the hydraulic conductivity. And so that's another very useful parameter that is now routinely measured with this tooling, is this index of hydraulic conductivity that you get by just measuring the injection rate and the back pressure. Week 2 was not so straightforward, and it's not because of lack of effort or the lack of the right team. We had the best team in the world, I believe, and these are Steve Chapman and others from the University of Guelph doing really very rigorous research quality field work. But we were stymied and challenged by difficult sampling conditions. We used lots of different soil sampling methods, but just were plagued by poor sample recovery. We finally modified a piston sampler so it was airtight and watertight, and that increased our sample recovery to about 65%. But that just highlights one of the biases associated with relying on soil cores for estimating if you have DNAPL present or not. In the end, we had collected 260 depth discrete subsamples, and those were analyzed, as I mentioned before, with the PID. A PID tool, the oil red O dye shake test, and the tabletop DyeLIF. And then 50% of those subsampled horizons subcores were sent to a lab for VOC analysis. And just a few photos just to impress on you that this was really excellent work done by Chapman and others, just very rigorous. And this type of work, in my experience, often isn't done at real sites, but we were quite fortunate to be working with this particular team. And this is PID screening, and then the very detailed subcoring and dye testing with the oil red O dye, showing the presence of a DNAPL in this area, but nothing below it, just because of the presence of a little silt layer. But very rigorous, detailed work, very time-consuming, and this level of detail can be obtained, in 30 seconds or 60 seconds maybe with this new DyeLIF tool. So just an example of what we found. And then the correlation with our DyeLIF tool, and this is the same on the left side. These two columns are the same, but just a different scale. So showing where there was a DNAPL identified in the DyeLIF tool. And then this other column is the response with the PID in a boring 1 meter away. So clearly some elevated responses at the same level. And then the visual screening with the dye shake test, we had negative responses. You either have a response or you don't. And at one particular horizon, we saw a positive response as well as positive responses at other depths. So actually a very good correlation between the DyeLIF measurements that were made very quickly, and then the confirmatory sampling done adjacent to it, a meter away, with both PID and the dye shake test results. So the correlation between DyeLIF and soil samples, getting to the conclusions, there was excellent agreement between the data from the cores and the adjacent DyeLIF logs. The DyeLIF achieved an excellent correlation with the oil red O visual shake test. There was a 100% match between the two for samples that were greater than 2.5% of the pore saturated with DNAPL, and we knew the saturations because we had done the analytical testing and petrophysical testing of the soil that we obtained from the soil borings. And then when we didn't have quite as good a match when we get to the lower saturations, but still 98% match between the two at pore saturations of less than 1% of the pore volume. And so the field detection limit, if you will, is between 1% and 0.1% of the pore saturation, so very, very low, but that will vary from site to site. Conclusions, and really this is, I think, is an impressive list that nearly 1,800 feet of soil was continuously characterized using the DyeLIF in just 4.5 days. DyeLIF has a thickness limit or detection limit in terms of the thickness of a layer as thin as about 1 millimeter. Below that it's a little iffy, but certainly 1 millimeter or thicker is easily detected with the tool. There is no response to dissolve phase VOCs, which is totally expected, and that's a benefit of this particular technology if you're really trying to identify if you have DNAPL, where it is, or confirm that you don't have it. The limit of detection is between 1 and 0.1% of the DNAPL pore saturation at this particular site. And so that produced an equivalent of an oil red O shake test every half a centimeter with an average daily production, if you will, of 395 feet. So in other words, the DyeLIF tool, it generated the equivalent of over 12,000 of these individual time-consuming standard traditional oil red O or color shake tests per day without any loss. We had 100% recovery, if you will, because it's a continuous measurement. Tracking the dye solution's flow and pressure reveals details of the hydraulic conductivity with depth, and the probe technology is compatible with both percussion rigs like geoprobes that are hammering, as well as CPT tooling and platforms, and it's recently now been married to a CPT sensor so that it now can be combined with other direct push technologies. So one of my last slides here, and that's a three-dimensional rendering of the DNAPL chlorinated solvent DNAPL source zone at the Lowell, Massachusetts site. And it looks a lot like some of the sketches and the models and conceptual models that we've had to live with for the last 20 or 30 years because we didn't know what's really at our sites. But I would maintain that this site in Lowell, Massachusetts is the best characterized residual DNAPL source zone in the world, and it was delineated in less than 1 week. My slide doesn't seem to be advancing for some reason. Oh, there it goes. Technology status. I'm happy to say that the report has been finalized and it's available online. And the technology is now commercially available from Dakota Technologies. Haley and Aldridge has no financial interest in this. It is a service and product being offered solely by Dakota Technologies. And at the bottom is a URL where you can find more information about it. Or you could just Google DyeLIF and that'll take you to the Dakota site. New dyes are being tested this week and kind of it's an ongoing program. And according to Randy San Germain, a new dye referred to as Venom is really fabulous for increased enhancement factors, and it really opens up this technology to other kinds of NAPL contaminants like pesticides, PCB oils, and other things. So it's an exciting time, and I think we're just starting to open up the opportunities with using dyes in combination with laser-induced fluorescence. I would like to acknowledge the team, which is Dr. Adrian Fury at Haley and Aldridge, Randy San Germain at Dakota Technologies, Beth Parker, and Steve Chapman. And for more information, that's the URL to download the final report. We are working feverishly on a manuscript to submit to a peer-reviewed publication. And there's my email address and my phone number if you'd like more information from me. So with that, thank you very much.
Great. Thank you, Murray. I'd like to remind our audience to submit questions using the chat box on the left-hand portion of the screen. We have received a number of questions on this first presentation that Murray will now answer. So Murray, first question from the US EPA. Is this technology available commercially yet, and how does the cost compare to LIF?
Yeah, thanks, Rula. The technology is commercially available from Dakota Technologies. And again, just Googling DyeLIF in Google, that'll take you to Dakota Technology. And the cost of it is really pretty incremental. It's a few $100 surcharge in addition to standard LIF tooling. So it's $1,700 or $1,800 a day, something like that, maybe $2,000 a day. But Dakota Technologies can provide quotes for it. But it's really a fairly nominal cost to add the dye to the system. And it is available throughout the U.S. and I think probably internationally through other collaborators.
Great, thank you. And at the example site that you discussed, this is a question from NASA, did you have an existing subsurface model of DNAPL distribution in the area you sampled so that you can compare the results of your sampling? And if you did, how closely did the existing model come to what you found?
Yeah, good question. And we did have a pretty robust conceptual model of the site already, which is one reason we wanted to work here, because we thought we would have some conclusive results. And the depth of the DNAPL was pretty well defined, not by probing in the source area, but by the transect of multi-depth sampling that was done down gradient. So projecting back to the source area, people felt pretty comfortable that they did not have DNAPL, below a depth of 75 or 85 feet. And so there was DNAPL detected at many different locations and at many different depths. So the general configuration that we outlined made really perfect sense with what was known before, but just a fraction of the insight and knowledge of the extent in 3 dimensions of the DNAPL was known beforehand, which is why this technology is so valuable, because we completed the 3-dimensional characterization in less than a week. But it was consistent with what their hypotheses were in their conceptual model, but now their conceptual model is much more robust as a result of the work that was done on this project.
Great, thank you so much. Can you tell us if there are false positives, for example, due to the soil type?
Yes, that's a good question. Also, there are false positives, and especially from what I understand with limestone and shell hashes, so calcium carbonate rich soils, sometimes there's an innate fluorescence with those materials. Randy St. Germain has educated me, but he's really truly the expert on this, and he has developed various filters and algorithms to separate out the fluorescence caused by those soil materials from a signal from a contaminant. So contacting Randy for more information about that would be the best way to get more information. But it does happen, but it can be filtered out.
Thank you. And can you tell us if there are geographic limitations to the use of this technology?
Yes and no. I mean, it is now pretty widely available throughout the U.S. There's a lot of partners that Dakota has, different direct push partners, and that firm has expanded recently. So it is available throughout the U.S. without any problem at all. Internationally, it may be a little bit more challenging, but MIP tools are now available throughout the world. So I think it's just a matter of time that this LIF and DyeLIF tool will be available internationally, but certainly it's available throughout the U.S.
All right, and a question from the academic sector from MIT. Can you tell us if this method will work in high organic carbon soils and sediments? Yes,
it's really it is sensitive only to a separate phase product. So advanced through different earth materials, including very fine-grained soils, has proven to be not a problem. And LIF is widely used throughout the United States and throughout the world for coal tar, creosote site characterization, MGP wastes, and a lot of times that's in quite fine-grained soils along coastal areas, and its soil type is not a big problem as long as you could advance direct push tooling through the materials.
Wonderful. And maybe one more question or two before we move on to our second speaker. What is the thickness of DNAPL that can be detected with this tool?
As I mentioned in the talk, it's about 1 millimeter, and that's a function of the sampling rate and a lot of the above ground detection equipment, and that actually was improved significantly during the course of this ESTCP project. So probably at the 5 years ago, it might have been about a centimeter, but on our project, with the advancements made in the optical tooling it's down to about 1 millimeter. But Dakota Technologies and in particular Randy Saint Germain could shed more light on that.
All right, thank you. And a question from EPA. Are there any regulatory requirements regarding the injection of dyes in the subsurface?
We haven't encountered any at all, and that was one area that we were particularly attentive to in this research project and this demonstration project. And we haven't encountered any regulatory hurdles with that. It's a very small amount of a hydrophobic dye that's injected into the subsurface into a contaminated source area. These are non-toxic dyes used in the textile industry, and they're not water soluble. We actually did leaching tests and had NDs for every VOC and semi-VOC. So it's immobile in the subsurface, and it would only partition into a DNAPL phase, not into water.
Thank you. And one question from the Navy. Besides the presence-absence analysis, does the DyeLIF tool provide other chemical characteristics, specifically physical phase, like dissolved versus free product, the concentration, and the kind of chlorinated compound?
Yeah, so it only detects DNAPL. It will not detect dissolved phased or vapor phase. And that's the a strength of the tool, because it is that's the purpose of it, is to delineate source areas where there is residual DNAPL, or if you're trying to prove that there is no DNAPL, this is the right tool. So it only responds to DNAPL, not other phases. And then saturation, it doesn't tell you the saturation. We determined that because we had nearly co-located soil samples and could correlate the response to the saturation. The last part of that question is, does it provide insights on the nature or the type of contamination? And yes, it does. We found from our laboratory testing that different types of DNAPLs responded differently to dyes, and then we could select different dyes to target and identify different types of chlorinated solvents. So we've had the discussion that there might be actually, and maybe a new ESTCP project would be to go out to a site with a handful of different dyes where you have a release of mixed DNAPL, and use the different dyes in combinations to delineate where you have different types and different releases of different DNAPLs in the subsurface. So it's, I think, really just the beginning of an exciting time of enhanced forensic analyses using dyes in combination with laser-induced fluorescence to do a much better job of delineating the nature, extent, type, saturation of residual DNAPL and LNAPL in the subsurface.
Great. Thank you so much for a great presentation. We'll have another opportunity to engage you in responding to questions towards the end of the webinar, but it is time to move on to our second speaker. And it is now my pleasure to introduce Dr. Andrew Jackson, who is a professor of civil and environmental engineering at Texas Tech University. His research interests include evaluating the environmental fate of a variety of military contaminants, including perchlorate, RDX, and chlorinated solvents. More recently, his work has focused on applying and expanding passive sampling technologies to support site management. Dr. Jackson received his BS degree in biology from Rhodes College, and then his MS and PhD degrees from Louisiana State University in engineering science, with an emphasis in environmental engineering. And with that, I'd like to turn it over to you, Andrew.
Great, thank you. Well, it's really great to be here and have a chance to tell you about a new technology that we've been working on that we think will greatly aid to the toolbox in site characterization. So I'm going to talk a little bit today about why we need high-resolution site sampling, a little bit about how the passive sampler works, the different functions it can serve, and then try to focus on field results from a demonstration that we did contrasting the results from the passive profiler with more traditional measures of site assessment. So the problem we're really trying to focus on is the problem of heterogeneity in contaminated sites, particularly chlorinated sites. And so traditionally, wells have been used to monitor concentrations, biogeochemical conditions, microbial populations, although there are certainly many other tools available. But regardless, almost all the other technologies are dependent upon at least to some extent, on the hydraulic conductivity. How well does water flow through each formation? So for instance, in the case where we have traditional large screened wells, this well screen is going to pull primarily from the most permeable regions, and so you're not going to get very good information about low permeability zones. Discrete wells do a better job because they can obviously be tailored to a more confined interval. But even then, as long as you cross two zones, you're still going to pull primarily from the more permeable zone. And in some formations, the zones are so impermeable that you can't produce water. And so the idea that we had was to basically adapt a technology that's been used for sediments to groundwater applications in order that the information that you want to receive is not dependent upon hydraulic conductivity. So a direct push technology that can be used at high resolution and be able to return data desired at, regardless of the hydraulic conductivity. So what we were out to do was develop a direct push technology that could passively evaluate the concentration of chlorinated solvents individually, the groundwater velocity, geochemical activity, and by that I'm kind of lumping everything you might want to know about the geochemistry. So concentrations of electron acceptors, dissolved organic carbon, conservative tracers for modeling, really anything you're interested in terms of the biogeochemistry. In addition, we wanted to be able to look at microbial community analysis and then also be able to understand the isotopic composition of the chlorinated solvents at each depth. And so to do that, we can you go to slide 56? Developed a sampler that would, there we go, sorry, had a little hiccup there. A sampler that could be direct pushed. So this is a 4-foot long stainless steel sampler. It has 5 sample increments per 4-foot length, so about every 10 inches you get a full set of data. There are 3 types of cells in each increment. There's a cell that's designed to basically be a microbiotrap. So bioset beads are put in the cell. The bioset beads can be used for quantum array analysis or any other molecular technology you want to use to look at the microbial populations. And then they can also be used to look at the isotopic composition of the chlorinated solvents. There are 2 cells, duplicate cells, that are used for looking at the concentrations of any dissolved species, whether that's chlorinated solvents, electron acceptors, anything that you're interested in. And then there are 4 cells in each sample increment that are used to determine velocity based on the relationship between a mass transfer coefficient of a conservative tracer with the velocity in the Porewater. The sample cells are filled with water. They're separated from the sediment by a 0.45 micron porous membrane, a nylon mesh, and a steel mesh to protect the membrane from puncture, and then they're secured with a stainless steel plate. And you can stack as many of these increments as you want to sample whatever depth interval you're interested in. So a little bit about how each of the sample cells works. The equilibrium Porewater sampling is an old technology. It's been used for decades. Essentially, you have a reservoir that contains water. The water is separated with a porous membrane from the sediment. And so anything that's dissolved in the sediment will diffuse into the sample cell, and over a period of time, the concentration in the sample cell will match the concentration in the sediment. These samplers are designed with about a 3-week equilibration period. That is tunable. You can shorten that if you want. The only downside to shortening it is you normally use lose a little bit of sensitivity. Pore water velocity is determined by a relationship between the velocity and a mass transfer coefficient. So in 4 cells of varying specific surface area, we have a bromide solution, which is used as a conservative tracer. And the bromide will migrate out of the cell into the pore water to equilibrate. The rate of that equilibration is dependent upon the time of deployment, the specific surface area, and a mass transfer coefficient. The mass transfer coefficient is directly proportional to the velocity in the pore water. And so at a single time deployment, by varying the specific surface area, we can get robust estimates of the mass transfer coefficient. And then using a laboratory relationship between the velocity in the pore water versus the mass transfer coefficient, we can be able to have a relationship that allows us to predict velocity based off the mass transfer coefficient. And we've looked at this in a lot of different ways. And so we've evaluated the deployment time and also the sampler rotation. So whether that's directly into the flow, 90 degrees to the flow, or 180 degrees to the flow, and there's really no effect of those components. Again, for the microbial population and the isotopic composition, we've essentially just used an existing technology. So many of you are probably familiar with standard biotraps that are filled with bioset beads. We basically just found a way to miniaturize these. We have a small compartment in which the beads are placed. There's a stainless steel mesh placed over this, and then a cover plate to secure it. The beads will basically absorb microbial communities and chlorinated solvents over the 3-week equilibration period. When the sampler is removed, the beads can be removed and shipped for commercial analysis using, in our case, we use the quanta array analysis, and then also evaluated the isotopic composition of the chlorinated solvents by CSIA. So now I want to move on to the field test, the site assessment. We've done this at 2 different sites, Fort Dix and then the Naval Air Station at Alameda, or the formal Naval Air Station, I should say. And I'm going to focus on the Naval Air Station field demonstration today. One thing I want to point out is that the site we were working on has been heavily studied. It's a fairly small site. It is about 10 feet by 10 feet, so there's a lot of instrumentation in this small area. It includes both multi-level wells in the blue, more standard interval wells. These are 3-foot or 10-foot screens. The multi-level wells are 1-foot screens, and I believe there are 7 of those at each depth. We also did direct push technology. So we looked at using the membrane interface probe and the hydraulic profiling tool at each location in which we used our sampler. We took soil cores at each location that we put our sampler, and we installed 3 samplers at the site. 2 of them were 12 feet in length, and 1 was 4 feet in length. And so the idea was to evaluate how well those worked against standard technologies. And so to give you a little idea how this works, the samplers are prepared in the field. They're essentially just assembled in troughs filled with deionized water spiked with a little bit of bromide. And so here are 2 samplers that have been prepared and are ready for insertion. And you can see how we just basically use a coupler to stack the samplers to whatever depth is desired. And you can see the different cells in the picture. The samplers are installed by direct push, so this is just a geoprobe system to the depth desired. And then after a 3-week deployment, the samplers are removed by a geoprobe system and then sampled in the field. And the way we sample these is simply to use a glass syringe with a needle. We don't open them up. We use the needle to go right through the membrane. We remove the water from the sample cells, and they're placed in appropriate containers for whatever evaluation is desired. In this case, we were looking at chlorinated solvent concentration, so we used mini VOA vials, and then we were also interested in dissolved species like nitrate, nitrite, iron, sulfate, chloride. The bioset beads are removed, and they're placed in sterile vials and shipped for commercial analysis. The whole process is pretty quick. It takes about 15 to 20 minutes to assemble a sampler and about the same amount of time to sample it to remove all the water for the various analyses. So what technologies did we compare to? We compared to the direct push technologies, so the membrane interface probe for the PID and ECD. We compared the velocities to the hydraulic profiling tool, so the pressure it takes to force water to the formation and the electrical conductivity. We also compared the velocities to measurements of velocity using passive flux meters installed in the wells. We evaluated the concentrations, the CSIA and microbial populations in both the multi-level wells as well as the standard wells, and we also did soil coring. And so the first location I'm going to talk about, although keep in mind these locations are very close together, is the P3 location, in which we had 2 standard wells. These are 3-foot screen intervals, a multi-level well, a direct push technology, a soil core, and the passive profiler. And the second location, which is only about 6 feet away, is a multi-level well, a standard 10-foot well, the direct push technology, a soil core, and the passive profiler. All right, this slide's a little busy, I realize, so let me kind of walk you through it. The left graph is the concentration of cis-DCE with the depth below ground surface. And I want to point out that the X scale is in the log scale. And so the first thing I want to focus on are the red circles and the red triangles. These are the concentrations of cis-DCE measured in the equilibrium cells of the passive profiler. And so the vertical bars are either the standard wells or the multi-level wells in the green vertical bars. And so one thing to notice is that the passive profiler concentrations match very well with the well screen, the well data, even over about 5 orders of magnitude. So at this site, we were going from about 100 ppm of cis-DCE, and within about 4 feet, we're down at single-digit ppb levels. The X's are the soil core data. And so again, very good correlation between the concentrations in the soil cores and the concentrations in the water. And then finally, we have the results of the direct push technology, the PID result, and the ECD result. The direct push technology did a good job in identifying the first chlorinated solvent peak, but it did not do such a great job on the second chlorinated solvent peak. And so there was really no response from the ECD here, even with 100 milligram per liter concentrations of chlorinated solvents. For the isotopic composition, we had pretty good results between a standard biotrap placed in a well and the micro biotraps, and then the passive profiler and the well water removed directly from the well. For vinyl, same kind of story. I won't spend as much time on this. So again, we have the concentrations of vinyl predicted by the passive profiler in the red symbols. The concentrations predicted from the well in the discrete interval wells in green, and the 3-foot interval wells in kind of aqua. Again, very good correlation with those, even over multiple orders of magnitude. Soil core data matching pretty well for vinyl chloride. And again, the fact that the direct push technology, the membrane interface probe, kind of missed this lower peak that was present. For the compound-specific isotope results of vinyl chloride, again, pretty good correlation between the passive profiler and the nearby well screens. So the other nice thing about this technology is that it does more than just evaluate chlorinated solvent concentrations. It will also evaluate really any soluble species. And so those might be things like electron acceptors that you're interested in, nitrate, nitrite, iron, sulfate. It could be dissolved organic carbon. In this case, as an example, I'm showing you the concentrations of chloride as a conservative tracer and sulfate as an important electron acceptor at many chlorinated solvent sites. And so in this case, you can see that the chloride concentrations increased dramatically over the 15-foot interval that we looked at, from about 200 ppm to about 1200. They then drop sharply down to about 400 and start to increase. Good correlation between well data and the passive profiler data at all locations. And then to highlight one of the reasons we wanted to do this work is the results from a standard 10-foot well screen, in which the 10-foot well screen completely misses this very large concentration peak, the decrease and the increase, probably due to the fact that it's pulling water from a lower formation with higher hydraulic conductivity. For sulfate, again, very dramatic increases and decreases in concentration, good correlation between the passive profiler and the well data, and again, the fact that if you were using more traditional well screen intervals, you would not be able to see this drastic decrease, which, given that the chloride is probably due to some type of seawater intrusion, this rapid decrease before chloride decreases is probably related to sulfate reduction, so that wouldn't have been picked up. So basically the ability to look at very fine resolution geochemical conditions that could change over very small intervals. In terms of microbial analysis, there's a whole bunch of data that's returned from a standard quant array analysis. All this data is available that is basically a variety of microbial species or activities. I've plotted just a few of these as an example. So I'm showing total eubacteria, sulfate-reducing bacteria, methanogens, and then on the right graph, the concentrations of a few different dechlorinating bacteria. And one thing to keep in mind is we're looking at both the dashed lines, which are biotraps put in wells, and the solid lines that are well water removed from the well. So in this case, this is a biotrap that was placed in a well, and this is water from the same well. And then the dots, the red, black, or green dots are the results from the passive profiler. And so in the case of sulfate for reduction, you can see that the passive profiler data matches very well with a biotrap at the same interval, and pretty good relationship with the water, although we have to keep in mind that the water is measured as cells per mil, and the biotraps are measured as cells per bead, so not exactly apples to apples. The bigger issue there is probably that you're looking at relative changes in bacterial composition rather than absolute numbers. In terms of groundwater velocity, we wanted to compare our results, which are the black dots or the gray dots. We estimated groundwater velocities ranging from about 5 centimeters a day down to about 1 centimeter a day with other measures of groundwater velocity. So at this site, they've done quite a bit of pump testing and modeling, and the overall site average groundwater velocity was estimated to be about 2 centimeters per day, falling right in between our measurements. The passive flux meters that were placed in 2 wells measured velocities from 3 to 4, again, bracketing the concentrations, the velocities that we measured. And then the hydraulic profiling tool. So the electrical conductivity varied a lot, but unfortunately, while it should have related to the grain size, the salinity at this site changed so rapidly, I'm not sure that that result is very meaningful. But the hydraulic profiling tool, which is related to the pressure it takes to push water into the formation, basically indicated 3 relatively significant peaks. And the high pressure corresponds to a low conductivity zone, and at each peak, we measured our lowest velocity. So almost a direct correlation with the high pressures and low velocities, which gave us a lot of confidence that the velocities that we're looking at are at least reasonable, given that they bracket all the other measurements of velocity and also correspond quite well to the hydraulic profiling tool. So in conclusion, this was a startup project. It included a field demonstration, and we think we've been able to develop a new tool that we think will have quite a bit of capability to be able to generate very high resolution data sets that are pretty robust in terms of all the data included. So not only will it look at the velocity at high resolution, the concentrations of chlorinated solvents, microbial activity based on both the population and changes in isotopic composition, but also almost any biogeochemical information you'd want to look at in terms of dissolved concentration, so electron acceptor profiles, conservative tracers. The HRIP is structurally adequate for direct push, and so has the potential to help at a number of sites. The importance of the work, well, the nice thing that we think about this technology is that it's high resolution data, but it's independent from well production rates. So you're no longer dependent upon the hydraulic conductivity of the zone you're interested in. We think this should provide much better site modeling because of the higher resolution data. For remediation design, it will help better understand whether or not natural attenuation is occurring, and if so, in what formations. It could help look for the need for bioaugmentation, not just in general, but in very specific zones. It can be used to evaluate the impact of remedial activities. So if you bioaugment or you biostimulate with edible oil, did it get to where you needed it to go, and is it still there? Is it having the activity that you want it to have? And then probably most importantly, the impact of the low permeability zones. What's the potential for rebound? Where should you be putting your wells? And what's the fate of the chlorinated solvents trapped in these low permeability zones? And I'd like to acknowledge a lot of coworkers that help with this: Paul Hatzinger and Paul Koester-Van Gross and Mark Tucker at CBI, Danny Reibel and Stephen Morris at Texas Tech, and then most of all, Haley Schneider, who was the grad student that's worked on this for the last 3 years and was really instrumental in helping us develop it.
Wonderful. Thank you so much, Andrew. We've received a number of questions. The first one is from the Massachusetts Department of Environmental Protection, and it's related to how you decontaminate the sampling cells. Can you please address that?
Sure. So, this was a demonstration project, and so we haven't had a lot of experience turning these around in the field for, let's say, redeployment the very next day. But the samplers are stainless steel, and they're pretty tough. And so any kind of standard decon technique is probably going to be fine. In the lab, we wash them with soap and water, and then ethanol or acetone, and then we basically rinse and deionize water. If you were going to turn these around in the field to be redeployed immediately, you probably have to obviously develop some kind of procedure that everyone was comfortable with. But they could also be even heat decontaminated if you needed to be, but that would obviously have to be done somewhere else.
Great, thank you. Do your hydraulic data represent a snapshot in time, or can you also track changes over time?
For a single deployment, you're looking at an average of the velocity over that time period. And so if you're wanting to look at changes over time, you would have to do multiple deployments. So you'd have to put samplers in, wait 2 or 3 days, put some more samplers in, wait 2 or 3 more days, put some more in, and then pull them out. Because each sampler deployment is an average of the velocity over the deployment time.
Thank you. And can you tell us if there are lithologic constraints on the use of this tool? Is it limited to the use of direct push technologies?
Yeah, so there are definitely some limitations. Clearly anything that can't be direct pushed is probably a problem, because drilling would make it very difficult to get the seal that we want to have, the direct contact between the sample cells and the sediment. You don't really want an annulus, because then you've got the potential for water to move up and down the sampler, and that kind of defeats the purpose. It's also restricted to obviously zones that you can get through reasonably well. If you've got to hard hammer for very long periods, the membrane is not indestructible, and so that can be a problem. And so we also have not evaluated the maximum depth we can go to. We've gone to 30 feet, but we have not tried to push it to depths greater. There's really no reason why it can't go, as long as I said the membrane's integrity is able to withstand the amount of force, the vibrations required to get through it.
Great, thank you. Would you recommend characterizing the geology of a site first, so you know where to place the samplers?
Well, I can see the samplers being used in a lot of different time periods during site evaluation. There's some great direct push technologies that can give you an idea of where you want to be looking, but once you've kind of narrowed down the locations, doing this kind of sampling prior to installing wells would go a long way to making sure the wells you install really give you the information you want them to give. And so it could be used at the onset of site evaluation. It can be used for site evaluation. It can be used to evaluate remedial activities or success. And so I don't really think it's dependent upon geologic information, although certainly that's always helpful. But combining the two would probably be the most useful. Obviously, if you're going to put this in, you have the capability of taking a core, and so looking at the lithology of the core with the information that the passive profiler sends back is added information.
Thank you. Can you tell us a little bit about your plans to commercialize the technology, and then what you anticipate the cost to be compared to commercially available technologies?
Sure. So right now we're looking into commercialization possibilities, Texas Tech and CBI. We would like to, obviously, this was a CERTA project, so more fundamental development, and we're hoping that it might be possible to get a ESTCP to demonstrate the use of it for site assessment as opposed to just a comparison. The costs are not going to be that much different than normal coring or other direct push technology. It's really just the time for a technician to prepare the samplers, the cost of pushing them into the formation and then coming back 3 weeks later and pulling them out. The analytical cost is comparable to the analytical cost from wells, and so it's probably in the ballpark of most other direct push technologies that people are familiar with.
Great, thank you. What is the maximum depth that the sampler can be deployed to?
Yeah, we haven't defined that yet. I mean, the limitation on depth is not so much with the sampler, but how hard it is to reach the depth. So, for instance, if you can core and then push the last 12, 15, 20 feet, then the sampler is not having to be hammered for 100 feet. But we haven't really explored that. That's one of the things we'd like to do in a follow-on project, is look at how robust not the sampler. The sampler is not really the issue. It's the membrane. And we've switched to a membrane that's much tougher, and we haven't had a problem with that membrane so far. But we have not tried to hard hammer for a continuous 50 feet to see how well the membrane holds up. So we've still got to explore the maximum depth. Right now, we've successfully done it to about maybe 30 feet. I can certainly see no reason why we shouldn't be able to get down to 50 or 60 feet, but it really depends on the formation you're in and how hard it is to penetrate.
Thank you, Andrew. A question from the Navy. Do you believe that your profiler can be adapted to work with packers in a fractured rock environment?
Yeah, it could. That's exactly the issue with using it in a kind of a hard rock environment, is that you want to make sure the sample cells are querying the domain directly outside of them and not getting vertical flow. So as long as you could develop a system in which you're sure you've prevented vertical flow, then they could definitely be used in a drill borehole type situation. That would be similar to other passive technologies that have been used in similar situations.
Thank you. Is there any disturbance of the samples that might affect the results during the physical removal of the samples, the samplers following the equilibration period?
Well, if by that the questioner means, like, is there an artifact of using the syringe to remove the water and then fill up the Lowell vial? Certainly there's a technique there involved that you've got to be careful with, just like with any type of volatile sampling, and that you don't want it to bubble a bunch of water to the sample, and you want to stream it down the side, and you've got to make sure you don't get an air bubble. But as long as the sampling is done in a reasonably efficient manner, we've done some lab studies to look at what the changes in concentrations are from taking 10 minutes to do the sample versus 20 versus 30 minutes, and those are pretty minor. The sample cells are covered with a very impacted layer of sediment that you have to go through, and so there's not a lot of gas exchange that can occur quickly. And so as long as the sampling is conducted in a reasonable amount of time after it's removed, somewhere between 15 and 30 minutes, there shouldn't be any artifacts of that. If it's not chlorinated solvents, then there's really no artifacts. A lot of the other species are stable regardless.
Thank you. For the concentration decay of the velocity tracer, is the rate measured in real time or after the removal of the probe?
after removal of the probe. So the probe is removed, and each one of those velocity cells, the water is removed, and the bromide concentration is determined by ion chromatography. And then the bromide concentrations the change in bromide concentration is used to determine the mass transfer coefficient, which is then used in a relationship with velocity to determine the velocity. So, once they're installed, they sit for 3 weeks, you pull them out, and then you get your velocity based on the results from the bromide concentrations in each sample set.
Thank you. And one last question before we re-engage Marie Einerson. Can the deployment time and or resolution be altered or changed?
Oh, sure. That's the great thing about the samplers is they're totally customizable. You may not be interested in microbial community analysis at every 10-inch interval, but you may want to have higher resolution for chlorinated solvent concentrations, or you may want to test for something else. And so the samplers are fairly easy to construct, and they can be tailored to any site requirements that the client wants. And so that also means that you could reduce the increase specific surface area and reduce the equilibration time. We've developed these samplers for sediments that can equilibrate in 2 days. I wouldn't propose that for groundwater sampling, but I think it's possible that you could get the equilibration down to maybe a week or 10 days without an issue, depending on what the concentration of chlorinated solvents you want to be in terms of your lower detection limit. So as you reduce the volume produced by each cell, you obviously increase your detection limit. These samplers were able to get to single-digit ppb, and so if I had half as much volume, I might not be able to get to that lower concentration.
Great, thank you so much. So I'm going to ask some broader questions from both of our speakers before we wrap up here, and we'll start off with you, Marie. So can you please summarize the next steps for your project? Marie?
Yeah. Yep, I'm on the line. The project is finished. We've finished our report, and actually the technology is now commercialized through Dakota Technologies. As I mentioned at the end of my talk, I think there's some exciting opportunities to advance the ideas and the concepts with different types of dyes and maybe different combinations of dyes to differentiate different types of NAPL in the subsurface. But we haven't proposed that yet, but don't be surprised to see an ESTCP proposal for something like that.
Thank you. And Andrew?
Pretty much the same answer. So, ours was a startup project, and so we're hoping to propose an ESTCP project where we'd be able to demonstrate the advantages of using the passive profiler versus traditional methodologies to assess a site. We certainly we're ready to work with anybody that would like to use the technology. We'd love to have the opportunity to work with them to demonstrate it at sites they might have. And so we're hoping to keep pushing this to have it become a standard tool in the toolbox for site assessment.
Thank you very much. And then what is the one message each of you would like to leave with our audience today? Starting with you, Marie?
That as an industry, we've learned that the subsurface is much more heterogeneous than we ever thought it was, especially in the vertical dimension, which is why you see projects and products like vertical profilers for soil characteristics or microbial communities or contaminant distribution. And that's given rise to a higher resolution of sampling at scales that are appropriate for understanding processes and things that are going on in the subsurface we're interested in. And that's now resulting in targeted in situ remediation programs that when combined with higher resolution performance monitoring truly provides diagnostic evidence of reactions and mass reduction. So it's an exciting time. Everybody thinks heterogeneity is a dirty word, but it's a reality, but fortunately we have an awareness and the technologies to better understand it, and now we can target remediation for specific environments and actually see what's going on and if it's working or not.
Thank you. And Andrew?
Well, Murray answered that really well. I'm not sure I have much to add, but I would just say that I totally agree that the heterogeneous environments require more complex solutions and more complex understanding. There's a lot that can be going on between abiotic and biotic processes, and being able to overlay co-located rich data sets increases our ability to understand what's going on, not just in general, but specifically at each depth, to be able to tailor remediation activities and to be able to evaluate the efficacy of those activities. And so better modeling and better evaluation is just going to give people much more confidence in the eventual result and what's really going to be needed to close the site.
Great. Thank you so much to both of you for a very engaging webinar. Our next webinar is on Thursday, June 1st, and is titled Classification of Military Munitions Using Electromagnetic Induction Data. Will feature Dr. Dean Kaiswetter from Acorn Science and Innovation. Registration is already open for this webinar, so please visit the CERTUP and ESCC page to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you could please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you so much for your attention.